Chemistry, we're beginning a short but important unit on the subject of gas laws. So gases are atoms, molecules, or ions that are separate from one another and often can float in the atmosphere. If the energy of motion, which is called kinetic energy, overwhelms the coulombic attractions between the molecules, in other words, there's more energy causing them to want to push apart than to want to attract to each other, then the molecules separate and exist as a gas or vapor. Now, gas in the sense of chemistry has nothing to do with the substance that people buy at a gas station to power their cars. It simply means unattached molecules, atoms, or ions that can float about, usually can float about. Sometimes they'll settle down on the surface, but often they can float. So, the study of gas laws treats atoms, molecules, and ions in gas state as though they're little balls. We don't care about protons, neutrons, and electrons. You're not going to hear us in this unit mention anything about them. Now, that doesn't mean that gases don't take part in chemical reactions, covalent bonds, and so forth. When we're studying the laws that are unique to gases, we don't think about those things. We don't think about the protons, the neutrons, or the electrons, or anything like that. Since the gas can either be atom, molecule, or ion, we use the generic term particle. So if you hear us talk about the word particle, it simply means either an atom, a molecule, or an ion. So gas particles don't randomly change direction. You must imagine that these particles are changing direction because they are encountering other particles that you can't see or the sides of a container. This gives gas particles their apparent random motion. Also, heating and cooling of the air or of the atmosphere can also cause particles to change directions. So gases can take part in chemical reactions. For example, the creation of water is two hydrogen molecules plus one oxygen molecule, both in gas form, can produce water in gas form. So water can be produced from hydrogen gas and oxygen gas. In this unit, however, we're only interested in how gas particles behave due to four factors: the pressure of the atmosphere, the temperature of the atmosphere, the volume of the container, that is the size of the container, and the number of particles, which we'll measure in moles. Pressure is the amount of force per unit area. Pressure can be thought of as the frequency with which the gas particles hit the sides of the container. So the more often they hit, the more force they hit with, the higher the pressure. The units of measurement for gas law variables are: temperature is measured in Kelvin, volume is measured in liters, moles is measured simply in the number of moles, and pressure has 5 different units of measurement, just because different areas of science adopted different units. So atmospheres, pascals, kilopascals, meaning 1,000 pascals, torr, and millimeters of mercury. So 1 atmosphere is the normal air pressure at sea level, where we are. So what you're feeling, the pressure that you feel on your body, and you may say you don't feel any pressure, but there's actually a substantial amount of air pressure on your body. That is considered to be 1 atmosphere because we are at sea level. The following are the conversions between units for pressure. So these are all what you feel at sea level, just measured in different units of measure. So 1 atmosphere. That's equal to 760 millimeters of mercury. And then some other branch of science decided they wanted to call that a torr, so it's 760 torr. It's equal to 101,325 pascals. And that's equal to 101.3 kilopascals. In the same way you made conversions between grams and moles, you can make conversions between any 2 measures above. So why are there 5 different units of pressure? Why there is 5 different units of pressure is something you don't need to understand, just know how to convert between them. So we'll do a couple of quick example problems. Examples of pressure conversions. So how many kilopascal in 2.3 atmosphere? So what you simply do is isolate the 1 atmosphere equals 101.3 kilopascal. You just pull those two out and make an equivalency. And then you can create a conversion factor. You need atmosphere to cancel out like that, and kilopascal to appear in the final answer. So there's 101.3 kilopascal for every 1 atmosphere, and that would give you 233 kilopascal. How many millimeters of mercury in 1.05 atmospheres? So you simply create an equivalency. 1 atmosphere equals 760 millimeters of mercury. So you create a conversion factor that gets the atmospheres to cancel out like that, and you end up with 798 millimeters of mercury. How many torr in 98,600 Pascal? So 760 torr equals 101,325 Pascal. So you need Pascal to cancel out. You need torr to appear in the final answer, and you get 739 torr. Again, these are all measures of the same thing, measures of pressure. So temperature is the average kinetic energy of the molecules. Kinetic energy is the energy of an object in motion. This translates into meaning that higher temperature increases the speed of the molecules. So if you turn up the heat on molecules, on gas molecules, they're going to move faster. Temperature is the average kinetic energy of gas particles. Kinetic energy is given by the formula, and you may remember this from physics, maybe not. Kinetic energy equals 1/2 the mass of the object times its velocity squared. So m equals mass, v equals velocity. You can think of that in chemistry as speed, although there's a technical difference that you do learn in physics. By increasing temperature, we increase the average kinetic energy of the particles. Since the mass of the particle remains constant, increasing the Ke increases the velocity of the particle. In other words, look at that formula up above. If you increase the number that Ke is, the number on the left side of the equation, and the mass has to stay the same because it's the same object, then the velocity on the right side has to increase. So increasing kinetic energy increases velocity. So the way to think of it is temperature increases kinetic energy, and kinetic energy increases the velocity of the particle. Let's say we have particles of 2 different masses in a container at the same temperature. This means they will have the same kinetic energy. So let's say we have the following 2 particles, and the mass of particle A is 2 atomic mass units. These are just fictional particles that we're making up here. And the mass of particle B is 8 atomic mass units. And let's say the kinetic energy that they are both experiencing is 16 joules. Joules is the measure of energy. So there's the formula we see again. So both particles have the same kinetic energy, 16 joules, so we can compute the velocity for each particle. So particle A, the Ke is 16, and that equals 1/2 its mass, which is 2, times the unknown velocity. We're trying to find the velocity squared. Now, you're not going to be asked to do this in class. I just want you to see this, or on a test. I just want you to see this as an example. So if you do the math on that, you solve for the velocity of particle A, you get 4. Okay, now look at particle B. It's also experiencing a kinetic energy of 16 joules, and that's going to equal 1/2 its mass, which is 8, times its velocity squared. So again, doing some algebra and solving for velocity, we get the velocity of particle B is 2. So what we notice is the lighter particle, particle A, is moving faster than the heavier particle, and that stands to reason that your common sense would tell you that that would happen. But what we're seeing is that particle B has 4 times the mass of particle A. That's 8 to 2, that's 4 times. But particle A, therefore, has a speed twice as great as particle B, 4 to 2. So let's see if there's a general law that can be derived from that. So the 2 AMU particle moves 2 times faster than the 8 AMU particle. So there actually is a law, and the 2 AMU particle moves 2 times faster than the 8 AMU particle. This leads to the following relationship for 2 gas particles called Graham's law of effusion. And we'll define what effusion is later, but it's generally just the movement of gas particles. So the speed of the lighter particle compared to the heavier equals the mass of the heavier over the mass of the lighter. You take that ratio and then you take the square root of that. So if we do that from our last problem, the heavier particle was 8, that was B. The lighter particle A was 2. 8 divided by 2 is 4. You take the square root of 4, you get 2. Okay, so you can see we get the same result from this formula as we got from looking at the kinetic energy formula in the previous slide. So that's called Graham's law of effusion. Okay, temperature. You may have had some experience with this in the past. So there's a scale that you're familiar with, we talk about all the time. It's the metric system scale. It's called centigrade. And basically the centigrade scale was defined that 0 degrees is defined as the freezing point of water. 100 degrees is defined as the boiling point of water. And then it's just broken into 100 equal increments in between 0 and 100, and those are called degrees in the centigrade scale. Now there's another scale that scientists use. It's called the Kelvin scale. Absolute 0 is the lowest possible temperature in the universe. It is 0 on the Kelvin scale and negative 273 centigrade on the centigrade scale. A degree on both scales is the same change in kinetic energy. The only difference is what each scale defines as 0. So if you look at the two scales, look at the freezing point of water and the boiling point of water. It's 100 degrees difference between the freezing point and the boiling point of water. If you go over to the Kelvin scale, the freezing point of water is 273 and the boiling point is 373, so that's also 100 degrees on the Kelvin scale. In other words, a degree on the Kelvin scale is exactly the same amount of change in kinetic energy as a degree on the centigrade scale. The only difference between the two is what they call 0. And the Kelvin scale was a scale defined that 0 really meant 0. There are no negative numbers on the Kelvin scale. It's the lowest possible temperature in the universe. What it means is that an atom loses all of its energy, its electrons just collapse into the nucleus, and it has no motion anymore. That's 0 on the Kelvin scale. So to convert that over to the centigrade scale, where 0 is the freezing point of water, that would be negative 273 degrees centigrade. So just look at those two scales and see how they compare. 100 degrees is 100 degrees on both scales. The difference is what they decide to call 0. So the centigrade scale has negative numbers. The Kelvin scale has no negative numbers. Okay, so here we see the two scales side by side, the centigrade and the Kelvin scale. And to convert from centigrade to Kelvin, you use the formula Kelvin equals centigrade plus 273. So just start over on the centigrade scale and start at 0. And if you add 273, you go over to the Kelvin scale. That will give you 273 Kelvin. If you want to go in the other direction, you want to go from Kelvin to centigrade, let's look at 373 Kelvin. So you take Kelvin, you subtract 273, and that would give you 100 on the centigrade scale. So it's just a simple formula to do that. By the way, one minor point, not really important, but I'll just mention it. When you're talking about centigrade degrees, you say degrees centigrade, but you do not say degrees Kelvin, even though it would seem logical to do so. You just say kelvins. So 0 degrees centigrade is equal to 273 kelvins. If you do say degrees Kelvin, nobody cares, but I just thought you should know that. So here are some simple examples. Convert from 25 degrees centigrade to Kelvin. 25 plus 273 is 298. That's one you're going to see a lot, by the way. To convert negative 35 Kelvin centigrade to Kelvin, so it's negative 35 plus 273 is 238 kelvins. Convert from 313 Kelvin to centigrade, so 313 minus 273 gives you 40 degrees centigrade. And convert from 260 kelvins to centigrade, so 260 minus 273 would be negative 13 degrees centigrade. Just remember there are no negative numbers on the Kelvin scale, and the number on the Kelvin scale is always going to be bigger than the number on the centigrade scale in case you start to get confused. Volume is the amount of space an object occupies in 3 dimensions. So in some cases the volume can change, such as with a balloon. In other cases the volume can be fixed, such as a glass or metal container. Volume is measured in liters in chemistry, and often milliliters. So 1,000 milliliters equals 1 liter. You've come across that conversion a number of times. So convert 467 milliliters to liters. So 467 milliliters times 1 liter for every 1,000 milliliters will give you 0.467 liters. A shorthand for that is to go from milliliters to liters. Just take the decimal place and slide it 3 places to the left. So you go from 467 to 0.467. The reason that might be important is you're going to do this conversion a lot. You do your measurements in the lab in milliliters, but the formulas, as you've seen, for solutions call for things to be measured in liters. So here's an important relationship between centimeters and liters, that 1 cubic centimeter, that's centimeters cubed, you take a centimeter in 3 dimensions, and that equals 1 milliliter. Usually we use cubic centimeters for solids and milliliters for liquids. Okay, this is the big formula for gas laws. There's one major formula that relates the 4 variables of gases, and it's called the ideal gas law. And what it says is that pressure times volume equals the number of moles times R, which is called the ideal gas constant, times the temperature. So P, V, T, and N have been previously defined previously. Pressure, volume, temperature, and number of moles. R is called the ideal gas constant, and it's that funny looking number, and it's got those funny units of measure. It's liters, atmospheres over moles, Kelvin. What you can think of the ideal gas constant as doing is does 2 important things. It tells you what units you have to be working in. So for volume, you have to be working in liters. If you have your volume in milliliters, you're going to have to convert it to liters before you use this formula. Atmosphere, pressures has to be in atmospheres. It can't be in pascals or torr or anything else. Moles is number of moles, that doesn't change. Temperature has to be in kelvins. It cannot be in centigrade. So if you have anything other than those units, liters, atmospheres, moles, or Kelvin, you're going to have to make a conversion into those units. The other thing it does is it acts like 6 different conversion factors wrapped into one number. And what that means is if you're trying to find the pressure from that formula, it's going to make the units for volume, for number of moles, and for temperature all cancel out so that the only unit you're left with is atmospheres, which is the measure for pressure. So it makes all the other units cancel out just right, and you'll see that with some examples. 0.0821 liter atmospheres per mole Kelvin. The purpose of this constant is it cancels the units of measurement, so only the units of the final answer appear. So if you're looking for volume, it will produce just liters. Temperature, it'll produce just Kelvin. The ideal gas law is the central formula for the study of gases. An ideal gas is a gas in which the particles don't interfere with each other. They don't bump into each other significantly. They don't slow each other down. They don't cause each other to lose any energy. The ideal gas law is PV equals nRT. Pressure is in atmospheres. Volume is in liters. N is number of moles. And T is temperature in Kelvin. And R is the ideal gas constant. So think of the gas constant as several conversion factors wrapped into one number. R causes all units to cancel except the one needed in the final answer. So there's the ideal gas law again. Think of the gas constant as 6 conversion factors wrapped into one number. If you solve for temperature, T equals PV over NR. The gas constant R will cause all units of measure to cancel except Kelvin if you're solving for temperature, and that's the units of temperature. Okay, so what happens to pressure when volume is increased? And assume all other variables remain constant. So the N, R, and T are going to stay the same. Well, if you were to double volume, then the pressure would have to be cut in half. Otherwise, N, R, and T would not stay the same. They're constant, so they have to stay the same. So if N, R, and T remain constant, then as V increases, P decreases because the particle hits the side fewer times. So the relationship between pressure and volume is called Boyle's law. So these two particles, these hydrogen molecules, are moving at the same speed. But you can see that the one on the left is hitting the sides more often because the volume is smaller, even though they're going the same speed. So if you increase the volume to the size on the right, the pressure will decrease because the particle is hitting the sides less often, and that's called Boyle's law. What happens to pressure when the temperature is increased? So if you look at it mathematically, if the temperature goes up on the right side of the equation, let's say you double it, then you have to double something on the left side of the equation, in this case the pressure. So if temperature is doubled, the pressure will double. So if N, R, and V remain constant, then as T increases, P increases because the particle hits the sides more times. The relationship between pressure and temperature is called Gay-Lussac's law. So there you see the same two particles in the same volume. The volume is constant. The number of particles is constant, the same, but the one that has the higher temperature has higher kinetic energy and therefore moves faster. What happens to volume when temperature is increased? So again, look at it mathematically, PV equals nRT. If you increase temperature on the right, then the volume on the left has to go up. So again, if you double the temperature, you're doubling the volume, assuming that P, N, and R all stay constant. So if N, R, and P remain constant, then as temperature increases, volume increases. So this is the hot air balloon law. For the particle to hit the sides the same number of times, that is constant pressure, while moving faster, that's higher temperature, the volume must get bigger. This is called Charles' law. So think about that. You got the same number of particles there, one on one, or just think of that as 1 mole, 1 mole. That's N. R never changes. R is a constant. And the pressure is going to stay the same. The pressure is going to be constant in both of those balloons. That means each of those He atoms has to be hitting the side the same number of times. And if you count, they both are. They're both hitting the sides about 4 times every 2 seconds. Okay. But since the one on the right has a higher temperature, it's moving faster. In order to get it to hit the same number of times, the faster particle to hit the same number of times as the slower particle, you have to increase the volume. So again, if you count how many times those two particles are hitting the sides, they're hitting 4 times every 2 seconds. So that means they have the same pressure, but the one on the right is moving faster. Therefore, it must have to cover a larger volume in order to hit the sides the same number of times as the one on the left. What happens to pressure when the number of moles is increased? So again, mathematically, if N goes up on the right, let's say you double the number of moles, then pressure doubles on the left. So if T, R, and V remain constant, then as the number of moles increases, pressure increases because there are more particles hitting the sides. The relationship between the pressure and number of moles is called Avogadro's law. So you can see that this one H2 molecule is hitting a certain number of times per minute, for example. If you add a second one, then they're going to be hitting twice as often, so that's going to double the pressure. So doubling the number of moles doubles the pressure. And that takes care of our first lesson on gas laws. It's a little bit long, but the concepts are fairly simple.